Hello and welcome to this session of digital encoding for cryptographic keys. In this session, we will learn how we really store these big keys, what is the bits and bytes behind storing these keys, what is the different formats. I am Vipin Tripathi and consultant in IoT, DevOps and cryptography space. Thank you. So let's begin. Okay, so bit stream. So I will just start with very basics. Maybe some of you already know and can skip these slides. Just for the very beginners. So as we know, the computer stores everything in 1 and zeros, and these are big streams of 1 and 0 and one after the other, and they are stored in the disk. Now how we make out different messages, different formats from this storage, and that is one science of encoding and formats to store things. So as all of we know, ASCII characters, so each letter, each digit, everything on the keyboard is assigned some ASCII code, and it has an hex and binary value, and ultimately computer stores those hex and binary values. Suppose A has an hex value of 41 in decimal 65, and in binaries as you see on the screen. So this similarly different other letters, 127 characters are there. Now these are the printable characters. There are some non-printable characters as well, but everything has some ASCII code. Now so in the web pages, if you see URL, sometimes you have noticed there are some percentage 20, percentage 26 or different other signs. What are those? Actually those are space. So space is represented by percentage 20 in the URL, and that's just to ensure there's no spaces going in the URL. So we'll discuss more on it. Like this is the ASCII table, and if you see, there are so many characters starting from decimal 32 to decimal 126. This table represents various characters we see on the keyboard, and that is printable characters. Okay. Now what is ASN1? So many of these notations are you see SNMP or LDAP or many other things, even key, they are formatted as ASN1 notation. So this is the standard description language for defining data structures that can be serialized and deserialized in a cross-platform way. Because once you send something from one computer to the other, we have to first take out this bit of a stream, serialize them, and then through serial communication we send it to the other party. Other party can take this series of bits and bits, 1 zeros, and convert back to the message. So there should be some well-known format or agreement how I will send from one side, how will I receive from the other side. So that is ASN1 syntax notation. Here is one sample. You say some protocol definitions if you want to define. So it will start with big A, and then if you ask a question, that will be a sequence of tracking number, question number, and then the question. And similarly the answer will come again as a sequence, and in the sequence we will have the question number and an answer, and that's it. So this is one basic, very basic structure, ASN1 structure. How it works? So when you send my question sequence, suppose this tracking number 5, question is anybody there, if you convert it to the BER encoding, it will be this string of the bits or hex bits. So if you I will discuss a little bit more on the BER encoding. So all works in the TLV format. So it's tag or type, then length, then value, and it is explained here. So if 30 represents a sequence, since we are having a sequence of two things, one is integer, one is string, so is 30, and it says that sequence is being followed. Then 13 is the length of the octet of value that follows. So total 13 will follow, 13 bytes will follow in this sequence. And now if we read first one, it says 02 So 02 represents tag for integer value. So we know there is an integer value of length 1 and the value 5. That's it. Then we take another tag 16 and it represents a string and its length represented by 0e, and then all for 41 onwards is a message. And what is the message? Anybody that's there. And this 41 is for A, 6e for N, and so on. So this way, so we have converted one message to a bit of a string, and now same thing when it reaches the other party will assemble this into again this format, and you send it to applications. Another encoding can be XML encoding rules, where we can send the message in text format like this. Okay. So TLV, if you explain a little more, so type, length, and then value. Now how we'll store a big number? Suppose one big number has 4 bytes. Now which byte you will store first and which byte you store next, and what is the last? So that is one very basic question, because ultimately in the memory space you have to store one byte one after the other, because the memory address will represent to 1 byte. Now the big endian case, the most significant byte is written first, and then we write next, and the least LSB or least significant bits are written at the end. But in the little endian format, we first write the least significant byte, and then we keep on writing till the most significant bytes. So that's the storage. So here you see the same number can be stored. I mean, one number can be stored as 1, 2, 3, 4, 5, 6, 7, 8. Or if we write in a little endian format, then this will this. So we have to be sure what endian is used, and both parties have to follow the same. For your computer or for your OS, you can always know what is, like in this Ubuntu lscpu command will give you little endian. So I know that my least bytes are stored first, and then the next one, and the highest significant byte is stored at the last. Okay. Now if we discuss more on the types, so what are the types? As we see in 2 types, integer and a string in the last section. Now we have more types here, like boolean, you have octet string, you have bit string, you have null, object identifier, object descriptor, external, and so on. So each of these will have some tag number like this, and from the tag number we can write and make the TLV format. Now in the type, if you go more into the details, sometimes your number could be very big. So suppose in the initial octet, so we have tag class like primitive, or its classes like universal, application, context specific, or private, and then we have primitive or constructed one. So these initial 3 bits are used for that, and then we have tag number. Now the tag number, we have 0 to 30 value we can put. For bigger tag numbers, we can use the many octets, and following octets will have all 8th bit as 1, and then you can write the bits. And to make a overall tag value, you just combine all these bits in big endian format and convert it to a number. Okay. Now coming to the length. So next, after type, you have length. Now length can also be 1 byte, or it can go over multiple bytes. So how we store it? There are 2 formats, short format and long format. If we have 1 byte only, we can use in short format to represent up to 0 to 127 bits of length. But if you have bigger one, then you make 8th byte, the first byte, as 1, and if next byte is 0, means all these are zeros, then it is indefinite But if 1 and then you have up to 126 octets, these are octets, means following, suppose we have here 1 and here we have written 50, it means the 50 bytes after this byte will all represent the length. Okay, so these are bytes, how many bytes are coming which will say the value of the length. Okay, and similarly 127 it is reserved. So this is one example, and this is called the long format. So in the short form you have everything in the 1 byte itself. You can have length up to 127 in 1 byte itself, but if you have bigger length then you have to use the long form. In the long form you have to put the first bit as 1, and then following bits will tell how many octets or how many bytes will follow to tell the length. So here you see this is 10, 10 means 2, so there are 2 more bytes which will tell the length. Now these 2 bytes, so the first byte, and it's a big endian format, so you have, so use 00001 in 1 and then 101 and all this here, but you total combine all these bits and that will represent 435 content octets, means your message is 435 bytes long. Okay, so that way, so TLV, as we read TLV how it presents. Now there is one more case to represent some non-printable characters or other data which we encountered in the cryptographic keys, because once we move bit and byte, it could be become anything, and it could be a non-printable thing as well. So how you store and forward this kind of thing? So there is a base 64 representation where we convert everything to printable format. Okay, so there could be some bytes which are not printable, but we take some chunks of it, and from the series of bits we make some chunks which is printable and then keep on printing. So here is an example. Suppose this is a bit, a big bit string, which is hex 03BA and all. Now this bit has to be represented in base 64 representation. What we'll do, we'll take only few printable bytes. So I will next slide I will show exactly how to do it. But on Unix system, on Ubuntu system, you can also make any messages in this representation. So like this is my message. Okay, if you just install base 64 on your computer, on your Linux machine, and pipe with the base 64, you get this output. And to make it reverse, you just encode this and base 64 minus D for decode, and you get your message back. You can also write this base 64 message in width 5, so each line will have 5 characters only. So these are different ways of output for base 64. Okay, now what is base 64? So base 64, we go encoding, we take 24 bits. Okay, from big streams of hundreds or thousands of bits, we just take 24 bit groups, okay, of each input, and then represent and take 6 out of each and represent a character. Okay, so we make 4 groups of 6 bits from this 24 bits. Okay, and then we convert it to character. So if you come down to the example, so these are the big bit stream which we see. Now we take blocks of 24 bits, which make 4 6 bits segregation. So 6 bits. Now each 6 bit is represented by a printable character. So this 6 bit value is 42, this is 12, 15, 0, 32 and all, and this 42 represents Q, this 12 represents M, and so, okay, and 0 represents A. This is coming from the base 64 encoding table. Now whatever the bit is printable or not printable, we make everything printable by this. Now suppose if you are left out of some bits at the end, you don't have complete 24 bits at the end, then you just pad it with equal signs. Okay, so this is the table, base 64 alphabet table. Why it's called base 64? Because 65 in ASCII, if you've seen, represents capital A. Now we are starting this table from A itself. So before A, the 64 ASCII characters we neglect and start our counting from A, which is 65th. So we are discarding 64. So that is base 64. So we start with A, which is 0, B is 1, and so on. Okay, and last padding is equal. So we make use of this table to convert any string, anything, to the base 64 representation. So most of the keys you have seen, some RSA and certificate, they are in base 64 representations. If you see at the end, sometimes you see equal signs. So this is a big RSA key, and RSA key starts with the 5 dashes. Okay, 5 dashes at the beginning, then it says begin RSA private key or whatever public key, then 5 dashes, and at the end also it says end RSA private key with 5 dashes on the both sides. Now in between, this is the key. I have zoomed out the last part if it is not so visible. So this is the last part, and at the end you see some equal signs are there. What are these equal signs? As I said, equal signs is for padding. So if you are left out with the some shortage of bits at the end, and it's not making your 24-bit block, then whatever bytes are left, you just pad each byte with an equal sign. Like here you see 2 equal signs. It means 2 bytes. Just to brief touch on the RSA, so its public key is E, N, and the private key is D, N. Okay, E is for encryption, D is for decryption, and vice versa. And what is this? N is a very big number on which we're doing mod of our whole message. Okay, so and this big number N is derived from two large prime numbers, and they are multiplied, and we get this N number. But the beauty of all the cryptographic security is that if you know the N, we cannot get out the P and Q so easily. So that's why we may keep on increasing the N. So N 2048 and 10024. So whatever big size N you take, it becomes very hard to calculate the P and Q from the N. And that's the basis of the whole security of RSA or any public key system. Now if you want to decode RSA key, so you have this key as we've seen in the last slides. We have the key, and now if you want to read what is there, what is the structure of that key, you can do it by, so you just cat it and you remove this initial and header and footer which represents that this is an RSA key, and the rest of the message is the key, and you decode it base 64 minus D, so you get back your original message from base 64. It will be converted to your original bits, and then you again use OpenSSL ASN parsing to make it a printable kind of data in hex. Okay, so this is the command, and this is the structure of the key, which is representing, you see here, sequence of integer and primitive and those kinds which we just saw in ASN1 format. They are coming here. Okay, So that's it on this side. Now if you're confused what is encoding and what is encryption, is there any difference? Okay, so yes, encoding is not a secret thing. When everybody knows the rules of encoding, so they know this is first byte, second byte, how you store, where you store, everything is known, and you can always decode a message. But encryption is something encrypted with a key which is not known to anybody, and you cannot decrypt any message which is encrypted without a key. So you need a key to make sense of that encrypted message. Okay, so there is a difference between encoding and encryption. Okay, thank you. See you in the next video.